up before the break. We finished as much of an information theory as we're gonna use in this course. We just looked at the capacity of the channel, defined what it is, and kind of gave some limits on our communication. So let me draw a block diagram and show you where we're gonna be over next few lectures. So here's where we start. We have our source, and then we have a block diagram that I'm going to call analog to digital processing. That kind of encompasses everything we've done thus far. And this means sampling, quantization, source code, source encoding, and then potentially some error control coding, which is that controlled redundancy that we produce to increase the capacity of our transmission. Now, the next step is really up to this point, your information is in digital format. So you have information in digital form. What am I trying to say? Up to this point, it's all numbers. But you cannot really send numbers, right? I cannot have 1 and just throw 1 to the other side, right? I have to actually take these numbers, and since we live in an analog world, I have to take these numbers, translate them into some voltages, currents, waves, whatever may be the physical disturbance of the channel or of the medium, and send that physical disturbance to the other side. So this is typically done with your transmitter, and I'm going to say here that I'm going to take this digital information and bring it back into the analog world. And what this will be actually based on whatever is the sequence of the symbols we have here, or sequence of bits. We're going to be selecting some waveforms that we're going to be sending over to the other side. Now here's your channel, and we discussed different types of channels. So right now we're going to look at the simplest one, and this is going to be our AWGN channel. I'll just in a second let's talk about a little bit of channel. AWGN stands for additive white Gaussian noise channel, right? Now, this AWGN kind of tends to travel in pack, but every one of these has a distinct meaning that is not necessarily always associated with this channel. I mean, with a particular channel. I mean, every one of these is an independent attribute of a channel. Let's just look at what do these attributes mean. Additive means that the noise enters the system as an additive disturbance. Noise is adding to the signal. When I get to the end of the channel, I have a signal, but in addition to the signal, I have another, so to speak, signal, which I call noise. The noise is added to the signal. Now you say, well, how can it be otherwise? Well, the noise may be part of a different kind of distortion. It may be multiplicative, right? Or it may change some other, let's say if you have a phase modulation, the noise may add as a disturbance in the phase of your carrier. So that's a different type of noise. Here, what we have is the noise that is added to the signal as another signal that's of a certain statistical characteristics. The noise is white, which refers to essentially its spectral characteristics. It has a white spectrum in a frequency domain. It is flat in a frequency domain. What can you tell me about autocorrelation function of this noise? It's a delta pulse. So we have a noise that is essentially mathematical model for a thermal noise. Thermal noise can be assumed as white over a pretty large range of frequencies that we use in electronic communication. White and Gaussian is not the synonym, right? Those are two different things. White talks about its spectral characteristics. Gaussian talks about its amplitude characteristics. The noise can be white, but not Gaussian, and Gaussian, but not white, right? That doesn't mean the same thing. A lot of times, students would confuse those two. You can have a noise which is colored, but Gaussian. How do you get that noise? Let's say you take the thermal noise and you run it through a filter. Because it goes through a filter, it's not white anymore, right? Its frequency domain characteristic, power spectral density, is not uniform. It goes to 0 after the cutoff frequency of the filter. In a magnitude domain, when you filter the Gaussian noise, you end up with a Gaussian noise as well. So this would be Gaussian colored or band-limited noise. So this is what all of these things mean. What is not apparent from this AWGN acronym is that this noise is, I should say, let me just say it this way, AWGN channel is infinitely wide. In other words, what is not, what is kind of seen here by just connecting a straight line, but it's not in this acronym AWGN, is we put no restrictions on a band. We assume that our channel has a very, very large band. In how large? Sufficiently large so that it does not impact the signal in terms of filtering. It does not change the frequency characteristic of our signal, right? If I send a pulse here, I get pulse here plus some noise on the top of the pulse. But the edges of the pulse are not going to be rounded because my bandwidth is infinite. All the spectral components of my signal will go through the channel. Now, at the output here, we have to have a block that does recovery of signals. And then we have our analog to digital processing again. Well, actually, let me call it digital to analog. So this is our sync. Now, what our concern here in the next few lectures is going to be is from here to here. So this is what we're gonna be analyzing, and it will include essentially modulation and demodulation / detection in the presence of noise. So that's our goal here. We're going to assume that you're sending some bits here, and we're going to look into what will it take to actually recover the same bits that you sent at this point. Okay. So that's settings. Before we get to even address this problem, I need to introduce some math here. And essentially, you might have seen it in communication theory, or you might have seen it in some other classes. But it's a common thing where we look at our waveforms that we're signaling, and we develop the mapping between these waveforms and appropriate vectors. We actually start seeing our signals as vectors in some multidimensional vector space. And the analogy there is going to be complete, but I need to introduce some math that helps us understand how this whole thing works. The reason why we do that is really pragmatic reason, because you will see that what we used to, what is actually integration in our world, or correlation, ends up being nothing but the dot product in the equivalent vector domain. And what we do by that is we turn the calculus into algebra, and that's much easier to deal with it mathematically, but also much easier to understand conceptually what is happening there. So let me talk about geometrical representation of signal waveforms. Signal or signals, just signals. Here's the settings. I'm going to be looking at, this is our time axis, t-axis. And I'm going to be looking at some interval a to b, which I'm going to call interval I. And on that given interval, I'm going to assume that I have a certain number of signals. I'm going to designate them as S1 of t, S2 of t, Sm of t, and so on. How many of these signals I have? I have m, where m can be potentially infinite, right? So I can have infinitely many functions that I define, or signals that I define on this interval a to b. What we strive to do is to develop an equivalent world. So this would be your signal space. And we seek to develop an equivalent world where I would have some vector space, let's say with some x, y, z. And every one of these signals would map into a vector in this particular space. So this would be, for example, S1. This would be S2, Sn, and so on. All right. So I need to learn how to map this waveform into this particular vector. Okay. So first, let me define, I guess what I can say here on the outset is I can state a theorem that says something like this. Consider a set of continuous functions on interval a, b. This set, along with multiplication, I guess with addition and multiplication by scalar. Multiplication with scalar forms a vector space. So let me define a dot product in that vector space. So dot product definition. Let's say I have two Si of t and Sj of t. They are two functions out of these set of functions that I have on an interval a to b. Then the dot product between Si of t and Sj of t, which I'm going to use this notation, Si of t in dot product with Sj of t, is going to be defined as integral over this interval I, Si of t times Sj of t dt. Strictly speaking, I should really put the complex conjugate there, but this is the only time where I'm going to put the complex conjugate, because in our case, at least in this course, we're going to assume that both of these are real function of time. So then the complex conjugate of a real function is the function itself. But you will find this in other books where these Si and Sj maybe complex functions, in which case it is customary to define the dot product by putting a complex conjugate. So I'm going to simplify this right away as an integral over I, Si of t times Sj of t dt. So how do I take the dot product between two functions? I take the first one times the second one, and I integrate that over an interval I. Dot product translates these two elements, which are functions, but which I can call vectors in this vector space, and it will, for every pair of these guys, it will give me a single number. It will map a pair of vectors into a number which is the area under the curve of this integral within an interval I. It is, well, this I is this interval from A to B. It is easy to show that the following properties hold. So let me look at some of these properties. A lot of them are very easy to understand. Actually, all of them are very easy to understand. But as I go through these properties, and I'm going to be working them here, always keep one eye to its alternative interpretation, because by doing these properties, eventually I'm going to say, okay, look at all of these properties. This is the same as what I have in a regular vector space, where I'm looking at what we usually refer to as n-dimensional vector space. So, properties of the product, right? As defined over there. It is easy to see that this holds. Si of t in dot product with Sj of t is the same as Sj of t Si of t for every I and j. Do you see that that's the case? Why is this the case? Because the integral, it doesn't matter if it's Si times Sj or Sj times Si, right? If you integrate under the area under the curve, you end up with this. The second property, let A be a scalar, the real scalar, then I have that A multiplying Si of t in dot product with Sj of t is the same as Si of t in dot product with Sj of t is the same as Si of t A times Sj of t. Right? That's again trivial. If you write what this is in terms of the integral, and you write this one and this one, they all yield the same result. The third property is the distribution property. It says that S1 of t, Si of t, in dot product with Sj of t plus Sk of t is equal to Si of t in dot product with Sj of t plus Si of t in dot product with Sk of t. This is a distribution property. So let's just prove this one so that you get an illustration of how all of these properties can be easily demonstrated. So let's do a proof here. So Si of t in dot product with Sj of t plus Sk of t by definition is an integral over the interval I of Si of t multiplying Sj of t plus Sk of t dt. Right? That's by the definition of what the dot product means, right? But now you see that this integral here can be split into two integrals. Integral over I, Si of t times Sj of t dt plus an integral over interval I, Si of t times Sk of t dt. Well, what is this first integral? This is a dot product with SI of t, and there's j of t. And then the second integral is the dot product between SI of t and Sk of t. Right? Now, let's just so that go back to what I was telling you earlier. Just keep your one eye on this. Let's say I have this is from high school or somewhere long time ago. Let's say you have three vectors A, B, and C. What does the first property say? A dot B is B dot A. Right? You see that that's true here, right? So that's the complete analogy. The second property says some constant, let me say A times dot B is A dotted with B, and it's and you remember that this holds too. And if I have three vectors A, B, and C, you know this from physics or math or wherever you've seen this first time. This is A dotted with B plus A dotted with C. Right? These are all familiar relationships. What I'm doing here is I'm kind of showing you that if I define an interval and I look at all the real functions that are on this interval, with addition between them defined point by point and multiplication defined in the usual manner, then I can make this a vector space, which means that I can make this equivalent to a space that looks like this, just a regular vector space. Now, let me define a couple of things in addition to vector product, in addition to this dot product. So definition, I'm going to define a norm of a signal.
Professor, this area under the curve, is this the common area of the two signals from A to B?
It's the area of under the curve of the third signal, which is the product of these two.
Okay.
So when you take the product between them, you end up with a third signal, and then area under that signal is what we're talking about. So I'm going to define a norm of a signal. I'm going to say the norm of the signal S of t is going to be defined as S of t in dot product with itself, taking square root of that. So in other words, this is integral over I s squared of t dt. But this fellow here is our good old friend. What's the area under the curve of the square of a signal? Energy. Energy, right? So this is a square root of energy. So what is the equivalence? Norm of the signal is, I called it an energy. If we go back to this analogy here, I would say the norm of A is equal to A dot with A, taking the square root, right? Well, what is A in dot product with A? It's the magnitude of A times magnitude of A times the cosine of the angle between A and A. What's the cosine of the angle between A and A? Zero. Angle is 0, so cosine is 1. So this is going to be magnitude of A. That's the equivalent here. Well, whatever it is the magnitude, the distance from the origin for the original vector, for the simple vector here, it's analogous to the energy of the signal. So what is the energy? The square root of energy. So the energy is square root of the norm. Actually, the square root of energy is the norm of the signal. So that's one of the definitions. Now I'm going to define orthogonality. We're going to say S1 of t and S2 of t are orthogonal if dot product between S1 of t and S2 of t is equal to what? This is the integral between S1 of t times S2 of t dt, that's equal to 0. Okay. So now, when it comes to vector spaces, do you remember what is the base of a vector space? How do we define that? Yeah, like what is the base of a vector space? Let me first, I see that the notes here are kind of really straight and to the point. So let me introduce another definition here. Linear independence. Consider a set of signals let me call this Si, where I goes from 1 through n, or what is called linear combination. So I'm going to say A1 times S1 of t plus A2 S2 of t plus and so on plus A n S n of t. That's a linear combination. And let me call this L. Now, set of signals is linearly independent if L of t identically equal to 0 for every t is equivalent that A1 is equal to A2 is equal to AN is equal to 0. So that's a little bit convoluted definition, but it's actually quite simple what we're trying to say. Go ahead.
Excuse me, Professor. I'm kind of like confused with it. I'm kind of like confused. Why do we need to consider about the linear independence on these things?
Because I'm going to be using it all the time. Not right now, but I want you to understand this concept here. You have a whole bunch of signals, n of them, and you form their linear combination. 2 times first one plus 5 times second one plus and so on.
So we treat the signals like a vectors here, like a...
No. So far, I mean, there's equivalent definition for vectors, but I'm defining it now for signals. So picture in your head a whole bunch of signals, and I formed a linear combination.
Like that previous was 3 signals, S1, S2, and
S2, S3, and I mix them somehow.
Uh-huh.
And however I mix them, I'm going to get a new signal, right?
Right.
Right. So my question here is, can I mix them so that this new signal is identically equal to 0? Okay? And I can have 2 outcomes of them. I can either do it or I cannot do it, right? Some signals, when you mix them, they can cancel each other, and some signals, when you mix them, they will never cancel each other, right? If these signals, when I mix them, can cancel each other only if all of these A's are equal to 0. Essentially, for any non-zero selection of A's, I would never be able to cancel them. Then I call these signals linearly independent. If there is some combination of A's for which I can create L of t identically equal to 0, then these signals are linearly independent. So that's the strict mathematical definition. Let me really state it in simple English. If you have a group of signals and you can pick one of them and express it as a function of the others, then they are linearly dependent. If that is not possible for any pick, then the signals are independent of each other, right? Okay, so okay, so that's a definition here. So if I can just simply restating what I just said, if I can express one of the signals as a combination of the others, then the signals are linearly dependent. If there is no way that I can do that, then the signals are linearly independent. Okay? Now the question that I asked you before is this. Let's assume I have n signals, right?
Number of the signal.
Number of signals is n.
Okay.
Then the question is, if they are not linearly independent, right? Let's say one of them or two of them or however many of them can be expressed as a function of the others, then the natural question to ask is, what is the minimum number of signals that I need to represent all the signals in my set? Okay? And that's a very, very familiar concept to you guys. Let me just go back to my vector domain. Let's look at two-dimensional space. This is my I or EI, and this is EJ. And this is my S1, this is S2, S3, S4, S5. So how many vectors do I have?
5.
I have 5. Are they linearly independent? No.
No.
I can actually, how many linearly independent vectors I can create in this space?
Infinite.
2.
2.
This is a two-dimensional space, right?
Right.
As a matter of fact, you can see right away, every one of these vectors can be expressed as a linear combination of EI and EJ, right? I can say, for example, this one is this much of EI and this much of EJ. So it's a natural question to ask. If I have n signals, what is the base, these EI and EJ form a basis of this space, right? And every vector in this plane can be expressed as a linear combination of EI and EJ. Every vector out of this set, S1, S2, all the way S to 5, can be expressed as a linear combination of EI and EJ. EI and EJ form the basis of this vector space in the sense that every other vector can be expressed as a linear combination of these two. Now if I have n signals here, the question that I ask is, first of all, are they linearly independent? And if the answer is they're not, then the question is, how many vectors do I need to represent all of them, right? And the number of the vectors that I can extract, that I can use to represent these signals, will form the base of this signal set, right? So let's say I have m equal to 15, and it turns out through some way that I can determine that I can represent all of these 15 signals as a linear combination of 3 signals. Right? So then I can say that my signal set has 15 signals in it, but the basis of this signal set is 3. I have 3 independent signals that I can use to represent all of them. These are not uncommon concepts to you. You know, for example, we can represent any color on a computer screen by mixing 3 colors, right? So there are 3 independent things, and then we derive all the possible colors as a combination. So it's simple, the same analogy is what we're after here. Now the question is, if I give you a signal set, let's say n signals, how do I determine the size of the basis? Or how do I determine this number of the signals that I need to represent all of the signals in the set? There's a procedure that I'm going to demonstrate here that sometimes it's obvious, sometimes you can do it by inspection, but a lot of times you would actually do it through a procedure that's called Gram-schmidt orthogonalization. And let me go through that procedure, and we're going to go through it and see how you can determine the size of the basis of your signal set in a systematic way. So we need to separate the two. We need to separate the size of your signal set and the dimensionality of your signal set. So we can talk about, let's say, 2-dimensional signaling, where we have 16 symbols or 16 different waveforms in our signal set. But the 2-dimensionality means that each one of these 16 waveforms can be formed as a mixture of 2 other primitive waveforms, or we can call them basis waveforms or basis vectors. So let's go through Gram-schmidt orthogonalization so that we understand this a little bit better.
Excuse me, Professor. Just a simple question to you. I still don't get it. How do I relate between the signal and the vectors?
We still haven't got there. I'm giving all of these things because I assume that you guys have seen vectors before.
Yeah, I've seen that before.
So I'm kind of going ahead on me and saying, okay, this is like this, this is like this, this is like this. But after we go through this, then we'll see that there is a one-to-one match. And I will show you how you go from a signal space to a vector space by essentially doing the same thing you did in a regular vector space. If I have a vector, I get the coordinates. How do I get the coordinates of that vector? I project the vector, I take the dot product of a vector with the basis vectors, right?
Right.
So if I want to get how large is the coordinate on x-axis, I'm going to take the vector and take the dot product with ex.
But I believe whenever it comes with a vector, then you need to calculate the distance of the vector.
We'll define all of that, right? Right now we're still building the blocks, right? So let me first, let's do one step at a time. So right now I have n signals, or rather m, let's say m.
M.
And I'm going to try to find out, and I'm going to assume that these m signals are linearly dependent. And I'm going to try to extract how large is n to find the basis for this signal set. In other words, I'm giving you a whole bunch of, if you go back to my graph with vectors, I'm going to give you a whole bunch of vectors and ask you to find me 2 unit vectors that I can use to represent all of these vectors. Right?
But isn't that similar to determine whether we're in 2D space or 3D space?
No, this is exactly what we're trying to do.
It's
right?
just only 2D space, right?
No, it could
Well,
be
no,
3D
it can
or
be
4D.
any D space, right?
So are those your eigenvectors? Or
Yeah.
Eigenvectors of what?
No,
Eigenvectors has a matrix associated with it. There's no matrix. It's just looking at, it's a representation problem. I give you a whole bunch of signals, and I'm trying to say, well, these signals can be mutually dependent. So that means there is a much simpler building structure that I can use to build these signals. Why is this important to us?
for vocal.
Let's say you have, this is the data coming into my transmitter, right? And what will transmitter do is it will pick certain number of these bits, and it will put the waveform here, right? So this is, let's say, Sk of t. And if I pick another, let's say, let me just do this. So let's say this is Tn plus 1, right? So I'm going to be encoding certain number of bits at a time, right? And what will happen here is in this interval I will put this waveform, and in this interval I will put this waveform. So this is your Sn of t, and this is Sn plus 1 of t, and so on, right? So this is how the signaling works. You're going to translate your bits here into analog waveforms that you're going to be sending on the other side.
Right.
Now, in your set here, you're going to have Si of t available, where I is going to go 1 through m. So I'm going to have m possible waveforms that I can send. In a more simplistic case, I have encode 1 bit at a time, and for 1 I send a positive pulse, and for -1, for 0 I send negative pulse, right? But I can encode 2 bits at a time, in which case I need 4 of these S's, right? M needs to be 4. Or I can encode, let's say, 6 at a time. How many waveforms do I need then?
2 to power 6.
So what is it?
64.
64 waveforms, right? So I'm going to have m different waveforms. But to build these waveforms, how I'm going to do that? I actually can build them so that they're, let's say, all independent of each other, in which case they're all unique. Or I can take, for example, and make these 64 waveforms all derivative of a single waveform. I send either positive pulse or higher pulse or even higher pulse, and I have 32 positive pulses and 32 negative pulses, right? Each one of them essentially just a different magnitude of a single pulse. So the question that I'm trying to address now is I have m vectors that I need to transmit here, and the question is how do I make that vector? And I can make it out of smaller number of basis vectors. And I guess what the question is, if I give you these m vectors, how would you determine the size of that basis? And we do that through a process called Gram-schmidt orthogonalization, right? So if I give you a certain number of these Sm of t, you can follow a procedure and you can tell me, okay, I really don't need to build, to have all of these stored. I can build them out of 3, or I can build them out of 2, or maybe even 1 basis vector by performing magnitude scale. And depending on how large the size of your basis, we're going to be talking about one-dimensional signaling, meaning the basis of your vector space is one-dimensional, two-dimensional, n-dimensional, and so on, right? So that's where we're going. So let me just take the next step, and this is the step of basis, signal basis extraction. So this is your Gram-schmidt. Orthogonalization. Procedure. So consider a set of m waveforms. So let's say we have m waveforms, Sm of t, where this m goes as 1, 2, 3, all the way to capital M. And our goal is to find the basis of a signal set. You have a set of signals, and we're trying to find out how large is the minimum number of signals that I need to represent this, all of the signals in this signal set. So the Gram-schmidt orthogonalization is very algorithmic procedure. To determine that, your basis set, you're gonna start by picking up the first vector, first signal out of this set. And then you're gonna say the first basis vector psi1 of t is gonna be 1 over square root of epsilon 1 times s1 of t, where this epsilon 1 is integral over this interval I s1 squared of t dt. So the first basis vector, I'm just going to pick the first one from here, and I just normalize, divided by its energy, square root of its energy, which makes it a unit norm. If you look at the norm of this guy, if you take the dot product of this vector with itself, you're going to get 1. Right? It's going to be unit norm. So that's my first basis vector. The second basis vector, I'm going to determine in the following way. So this is, I guess, k equal 1. K equal 2. I'm going to say d2 of t is going to be s2 of t minus s2 of t in dot product with psi1 of t times psi1 of t. And then psi2 of t is going to be equal to d2 of t divided by square of energy 2, where energy 2 is going to be equal interval of d squared of t dt. So what is it that I'm doing here? I'm taking the next one out of this signal set.
Is that M or K?
Where?
Should the K be M?
Where? Here? K?
Yeah.
K equals 2. K goes all the way, well, yeah. No, this M is just, both of them are just running indices, right? So they don't have to, you can pick any letter there, right? You have, but these numbers are important. M is important, and then N is important that I'm going to talk about in just a second. But K and the little m can be anything, right? These are just running indices. So this is how you get your first basis vector. Once you have the first one, the second one you get through this process. You take the second of your signals, project it, or take the dot product with the first extracted basis vector, times the basis vector, and then you subtract that from S2 of t, and then whatever you get, you normalize that. Right? In general, for k, you get dk as sk of t minus sk of minus sum when I goes from 1 to k minus 1, sk of t in dot product with psi I of t times psi I of t, and then your psi k of t becomes dk divided by square root of epsilon k, where this epsilon k is an integral over I dk squared of t dt. This looks somewhat complex, but it's actually quite simple what you're trying to do.
So, Professor,
Mhm.
so the D2, we're just finding the projection of the first signal and the second signal? Is that what we're doing?
Yeah, this is a projection. Let me, before I go through an example, let's look at how we're gonna do this in a vector space, like a regular two-dimensional vector space. Let's say I give you one, two, let's say 3 vectors. This is S1, S2, S3. As a matter of fact, I don't need to give you all any of this. Just 3 vectors. And here's what I say. Find if these are independent and what is the basis of this vector space. Okay? In other words, find what is the minimum number of vectors that I need to represent these 3 vectors. And here's how I start. I say my first vector, psi1, is going to be S1 divided by square root of energy 1, right? Where this is your integral S1 squared of d dt. So that's my vector notation. In this is my signal, right? In my in a vector domain, I'm going to say psi1 is equal to S1 divided by the absolute value of norm of S1. So I'm going to take this S1 divided by its norm, and I make this like psi1. So that's my first basis vector. Now I say, okay, well, how do I form the next one? Well, let's say this is S2. So now I grab this S2, project it to this. So this vector here is going to be S2 in dot product with psi1, right? So this is this piece, right? And I multiply that by psi1, so this is this length here, and I subtract that from S2. So when I subtract that from S2, I end up with a vector that looks like this. So this is S2 minus S2 in dot product with psi1 times psi1. Right? This S2 minus this gives you this. Right? So this is my vector D2. Okay? And now in the second step of this extraction here, I take D2 and I divide it by its norm, right? So what I do is I make psi2 equal to that. So this is my psi2. Okay? Now what is the angle here?
They should make
90 degrees, right? They're by construction they're orthogonal. And also by construction they are of a unit norm. So the Gram-schmidt orthogonalization is going to give you what we call orthonormal basis of the space. Now if I take now S3 and I try to go and do this with S3, here's what you find out. This is S3 projected to the psi1. This is S3 projected to psi2. Is there anything left? If I take S3 minus projection of S3 to the psi1 minus the projection of S3 to the psi2, I get 0. So that means S3 can be expressed as a combination of psi1 and psi2. And I've reached the end of my signal set. Therefore, the basis of the signal set is 2. And there are 2 vectors, basis vectors, psi1 and psi2. So this is in a vector domain. This is what I'm trying to do in a signal domain as well. And to do that, to see how that works in a signal domain, let me give you an example where all of my, well, I'm going to work only with signals. So let's look at the example here. And I have 4 signals here. This is S1 of t. And this guy goes 1, 2. Then there is S2 of t. This is S3 of t. This is 1, 2, 3. This is 1 minus 1. Again here 1, 1. And the last one looks like this. 1, 2.
Is that S2 under the S1?
This is S2.
Okay.
So how large is M in this case? M equal 4. So I have 4 signals in my signal set. To relate back to this picture here, I can use, for example, this set to encode 2 bits at a time, right? If I have 0, 0 maybe, I send this. If I have 0, 1, I send this. If I have 1, 0, I send this. If I have 1, 1, 1, 1, I send this waveform, right? So I have 4 waveforms, but that doesn't tell me what is the dimensionality of this signal space. So to determine the dimension of this signal space, I'm gonna do Gram-schmidt orthogonalization. Here, the interval, just so that is equal to 0 to 3. Right, so even though these two guys end up at 2, the whole interval goes all the way to 3. So I'm signaling over interval from 0 to 3. So let's follow this procedure. So k equal 1, the first basis signal. I'm going to say psi 1 is going to be S1 of t divided by square root of epsilon 1. Epsilon 1 is going to be S1 squared of t dt. In our case, this becomes an integral from 0 to 2, 1 dt, right? Because when I square this, it only exists between 0 and 2, and square of it is 1, right? So so this is 2, right? So my psi 1 of t is 1 over square root of 2 times S1 of t. How does the psi 1 of t look like? This is t, 1, 2, 3, and this is 1 over square root of 2. So this is psi 1 of t. Okay, this is my first basis vector, or basis signal. Okay? Now let's look k equal 2. K equal 2. First, I need to take whatever is this signal here and subtract whatever is projection between this signal along the direction of the first extracted signal. So what I need to do first, say something like this. d2 of t is going to be s2 of t minus s2 of t in dot product with psi 1 of t times psi 1 of t. Right? So that's what first thing I need to do. Well, what is S2 of t in dot product with psi 1 of t? It's an integral over interval I, S2 of t times psi 1 of t, dt. Well, how large is this integral? We'll take this and multiply it with this and tell me what is the area under the curve. Okay, let's do it. So here's what I have. I have psi 1 of t, which looks like this.
Oh, can we change it to you? Okay.
That's the side one of t.
This is 1 over square root of 2, and this is S2 of t. So when I multiply, I have S2 of t times psi 1 of t, which looks like this. Right?
Right.
And this is 1 over square root of 2, and this here is minus 1 over square root of 2. But whatever is the case, what's the area under the curve? So this part here is equal to 0. So d2 of t, what can you tell me about these two signals? If their dot product is equal to 0, they're orthogonal on this interval, right? d2 of t is therefore equal to S2 of t, and my psi 2 of t is going to be essentially S2 of t divided by square root of energy of epsilon of S2 of t. What's the energy of this signal? If I square it and integrate the area under the curve, what do I get? So what is the signal? Energy is 2, right? So my psi 2 of t is going to be 1 over square root of 2 times S2 of t. How does psi 2 of t look like? My second basis vector, psi 2 of t, looks like this. 1 over square root of 2 minus 1 over square root of 2. So I have now extracted 2. So my basis is at least 2 by now.
Is this almost in like the linear system? The
Uh-huh.
first chapter of linear system?
I don't know if you noticed, but almost every other subject comes out of any other subject, right? So, because we're in the same general area, we just, this is an extension of linear systems, right?
There's only you just need to determine the area under the curve.
That's why this whole thing is so hard, the engineering, because nothing is ever disjoint. You cannot get out of the linear system and say, "Oh, I passed this exam, forget about it." What we learn in linear systems is here, and in communication theory, and in adaptive filtering, and in the DSP1, and in the stochastic signals.
So there will be like a signal with a curve, something like that, and then
There's some addition.
Yeah, on the meter, yeah.
on
Okay, so we have extracted the first and the second. So let's do the third one. The third one, in the first step, we're going to say d3 of t is equal to S3 of t minus S3 of t projected to the psi 1 of t times psi 1 of t minus S3 of t projected to psi 2 of t times psi 2 of t. Okay? Now let's do these dot products. S3 of t times psi 2 of t dot product is equal to what? I'm going to take this signal and multiply it with this signal and take the area under the curve. Now let's look at from 0 to 1, I'm going to have a negative pulse. From 1 to 2, I'm going to have positive pulse. From 2 to 3, I'm going to have 0. So, do you follow? Let me go again. So I'm taking a product with S3 of t and this one here. Now look at the interval between 0 and 1. It becomes negative pulse, right? With the magnitude minus 1 over square root of 2. This guy and this guy. Right? So now, watch them carefully, because I can write all of this, but I want to save some time. So between 0 and 1, you get a negative pulse minus 1 over square root of 2. Between 1 and 2, you get a positive pulse with 1 over square root of 2. And between 2 and 3, you get 0. So what is the area under the curve? 0. Right. So this one is 0. S3 of t in dot product with psi 2 of t is going to be equal, now I'm taking the dot product
Of the,
between S3 of t and this guy. Now you can see now between 0 and 1, you get a negative pulse with minus 1 over square root of 2, right? Now between 1 and 2, you again get a negative pulse with minus 1 over square root of 2. And between between 2 and 3, you get 0 again. So this, this ends up being minus 2 times 1 over square root of 2, which is minus square root of 2. Okay? So now, d3 of t is going to be equal S3 of t minus 0, I skipped, and then it becomes plus square root of 2 times psi 2 of t. How does this d3 of t look like? You have to take this signal here and add square root of 2 times that signal over there. So you see what happens. Square root of 2 makes this between minus 1 and 1.
Yeah.
Between 0 and 1, you're going to have positive pulse from here and negative pulse from here. So they're going to cancel.
Yes.
Between 1 and 2, you're going to have negative pulse from there and positive pulse from here.
Cancel.
They're going to cancel. And then between 2 and 3, you're going to have just S3 of t, because that one is 0, right? So d3 of t
1 over.
looks like this. What's the energy of this signal?
1.
1.
Right, so d3 of t is the same as phi 3 of t. So that's the third basis factor, right? Go ahead.
Why is it not like 1 over square root of
Give root 2 into.
It
Oh,
is.
because-
It's just the energy is equal to 1. It's already 1, right? Which is, psi 3 of t is equal to d3 over square root of epsilon 3. But epsilon 3 is the energy of this signal, which is 1.
Oh,
Right, so it's the same as is d3 of t. Okay? Now, so our basis is at least 3. Now, I need at least 3 signals to represent these. Right? This guy, and this guy. Now let's take a look at this one. And okay, yeah, you're right. So you can see, let me just do this. K equal 4. And I can write this and then we can see that. So you can say something like this. D4 is going to be equal S4 of t minus
S4 of t.
sum. K goes from 1 to 3. S4 of t in dot product with psi k of t times psi k of t. If you do these dot products, here's what you get. S1 of t in dot product with psi 1 of t is equal to square root of 2. S4 of t. S4 of t in dot product with psi 2 of t is equal to 0. And S4 of t in dot product with psi 3 of t is equal to 1. And when you say now D4 ends up being S4 of t minus square root of 2 psi 1 of t and minus psi 3 of t. And this is equal to 0. In other words, you can say S4 of t is equal to square root of 2 times psi 1 of t plus psi 3 of t. So what is it that I determined? I determined that this guy here can already be represented as a linear combination of the previously extracted basis vectors or basic signals. So in this case, my m is equal to 4. How large is my n? N is equal to 3. And I have 3 basic signals. This is my third one. This is my second one. and this is the first.
The first one.
So if I were to use this for signaling, the type of signaling I'm going to be implementing would be three-dimensional signaling, because I have three independent vectors, and I'm going to be forming my constellation space, or I'm going to be forming my signal set by mixing my three basis vectors, psi1, psi2, and psi3. You can express each one of these as a linear combination of these three that I have already mixed up. Okay? So I know the time is up, so let me stop here. We're going to continue next time by completing the analogy between signal space and